pleasure to introduce our panel speaker, Alex Lupsasca of Harvard, who will talk about extreme Kerr magnetospheres.
Thank you very much for the invitation. It's a great honor to speak here. I guess this is a very propitious time to start a new black hole physics center. It's a very exciting time because we've heard of black hole merger. It's the first time we detect gravitational waves. So this was the LIGO experiment. And it opens the door to a whole host of new experiments that are going to be done in the future. There's going to be more events at LIGO, and then we're going to have ELISA missions and other experiments. So we're going to get to hear a lot of black holes. And also, there's an exciting experiment called the Event Horizon Telescope, or EHT, which is going to try to not hear black holes, but see them for the first time, really take an up-close picture of a real black hole. Sagittarius A star is one of them, the one at the center of our galaxy that Lorenzo mentioned. And also M87, which is at the center of a nearby galaxy, which is it's much further away, but it's also a supermassive black hole, so it has about the same size in our sky. And there's really a pressing question, which is, what are we going to see? What is the black hole really going to look like? So just take a camera and snap a photo. What do you get? And so to really answer this question, very naively, you sort of need to know two things. One, what are the relevant fields that you want to discuss that are relevant around the black hole, and what are their laws? The effective laws that describe them. And so clearly, there's gravity, so the metric is one of them. As Lorenzo mentioned, there's an electromagnetic field, F mu, and you can consider various approximations where it's collisionless and described by MHD, or force-free, perhaps. And then there may also be matter, described by a stress tensor, etc. And then once you have the relevant fields and the effective laws, then you just have to solve them. Okay? And so this task is actually really, really hard. If you're an astrophysicist, then you can do a particle in cell simulation or whatever model you prefer, and you just put the equations on the computer, and you let it run, and you see what happens, which is great. It's perfectly fine. Perhaps we'd like to get some more qualitative intuition. So that's one reason to try and do better and maybe do some analytics. And the other problem is that there's a special situation where the black hole is extreme, and I'm going to talk a little bit about this, where actually the numerics are very difficult. They sort of break down. And there are many reasons for this. I'm not an expert in numerical relativity, so I'm not going to go into them, but perhaps a picture that, one of the factors that makes it so hard is that a rotating black hole usually is described by the Kerr metric, which I've written here because it's so nice. It's really quite fantastic that Kerr discovered it. And in fact, this takes care of this field here in our description, because we know that the universal solution that describes astrophysical black holes that are rotating is the Kerr metric, so that takes care of specifying the equation for this guy. This metric really has two event horizons. It has an outer event horizon, which is what we consider the physical one, but it also has an inner horizon, which is given by the choice of minus sign here. And so if you draw the Penrose diagram for the spacetime, first remember that the Schwarzschild Penrose diagram looks like this, where this is the event horizon RH. Now in the Kerr black hole, the situation is slightly different. And what happens, actually let me use R plus to be consistent, is that you now have an inner event horizon, R minus. I'm going to draw it as follows. And then you have a time-like singularity here. And the Penrose diagram doesn't close, so I'm supposed to tile this up and down forever. But at least naively, if you try to do a numerical simulation, you can't just cut off the part of the spacetime behind the horizon. You have to go a little bit deeper, just a few cells. And that's perfectly okay as long as you have an inner event horizon that shields you from the singularity. But you can see that there's a special situation here where A equals m. A is the ratio of angular momentum to the mass. It's the spin parameter that labels the black holes in this time wave solution. When A is equal to m, R plus and R minus coincide. So it's a degenerate situation where you only have one event horizon, and the Penrose diagram just looks completely different. It's a qualitative change. These two lines merge, and so instead what you have is R plus equal to R minus. This is us. And now you have your singularity here. And so if you try to go a little bit beyond the horizon, you're in the future light cone of the singularity, and so there's no determinism. So that's one of the many reasons why the extremal Kerr black hole is a little bit weird. So this is the case that I'm going to focus on because even the numerics are hard for this and other reasons. It just so happens actually that the analytics get very simple, or at least much simpler. And there's a whole lot of things, magical things that happen that help us do physics there. So I'm going to focus on this case. And I'm going to start out by telling you a few things about it, and hopefully I'm going to convince you that there's a special metric that you can write down to describe the throat of an extremal Kerr black hole, which is the neck metric. And I'm going to try to spend the next 15 minutes explaining why it's interesting and how it can be useful to do real physics. And then in the time that I have remaining, I will use the neck metric and show you some applications to infer to tell you about some of the physics around extremal black holes. Okay, so if you look once again at the Kerr metric, you can see that so A is the spin parameter, J is equal to AM, and the event horizon is located at this point. And you can see that if A were to be greater than M, this quantity would become imaginary. And so there would actually be no event horizon. You'd be violating cosmic censorship. And we think this is not allowed. So therefore, A must be less than or equal to M. And the black hole which saturates this bound, which is at A equals M, we call it extremal. And its angular momentum is then precisely M squared. So we believe that this is the maximal angular momentum that a Kerr black hole is allowed to have. And in fact, I didn't write the formula for the temperature, but this is a very special point in this Kerr family of solutions because the temperature of the black hole goes like R plus minus M. And so at extremality, the black hole really has zero temperature. So that's one of the funny things that happens. And I'm going to try to draw an analogy with condensed matter physics in a second, but spoiler alert, I'm going to argue that really this point in the family of Kerr metrics, A equals M, is a critical point at which TH goes to zero, the Hawking temperature vanishes, and we should therefore think of this as a critical point. And there's a vast literature in physics that tells you how to exploit critical points to constrain the physics, but I'm going to argue that this is an example of a critical point in astronomy, and we should just follow the usual recipe and extract some physical information out of this. So let me draw first a picture to better explain what's going on, and then I'll come back and write some equations to make it rigorous and keep everyone happy. But I think the picture is very simple and useful to keep in mind. So the picture I want to draw is starting with the Kerr metric in these coordinates, which are called the Boyer-Lindquist coordinates. I'm going to take a slice of t equals constant. Let's say t equals 0. And I'm going to specialize to the equatorial plane. So I'm going to take theta equals pi over 2. And then my metric will describe the surface parameterized by r and phi. And this is a 2D surface, so I can draw an embedding diagram into 3D. And I'm going to do this here. Now, if I were in flat space, if there were no black hole, I would just get a flat surface. But actually, if you use this metric, there's a black hole at the center at r equals 0, and what it does is that it deforms the surface, and you get a mouth, or a throat, which is the mouth of the black hole. Now, as long as A is less than M, so that you're away from extremality, this throat has finite depth. So it ends at some finite distance at the event horizon. But one of the special things that happens at extremality when A is equal to M, one of the things that makes this metric singular, is that in that limit, the proper distance down the throat, the proper distance down to the horizon, really diverges. So what happens is that you now get an infinitely deep throat. Eventually terminates at the event horizon, but that's infinitely far away. So in other words, if you take the Kerr metric, you have a black hole, and you make it extremal, if you look close enough to the event horizon, you're really in a region of high curvature where you can think of the spacetime as having become this long throat. And so pictorially, of course in a second I'm going to make this precise, but pictorially you can see that there's going to be an enhancement of symmetries. The original black hole is stationary and axisymmetric, and indeed you can see that it has two killing vector fields, dt and d phi. And those, of course, are still preserved in the throat. So on this picture, going around here is the phi direction, and then going down the throat is going along the direction of decreasing r. But you can see that if we just were to cut off the throat here and look at only this part of the spacetime, there would be an extra symmetry because now I have an infinitely long cylinder, and if I go up and down the cylinder, that's an isometry. So I'm going to actually write down some equations in a second to make this precise, but I think it's important to keep the picture in mind. The translation symmetry that emerges, translating up and down the black hole, physically is a dilation symmetry because it means zooming in or out of the event horizon. Incidentally, I should also say there's actually a further enhancement. So whenever you have an emergent conformal symmetry at a critical point, there's usually an infinite number of symmetries. I'm not going to use the infinite number of symmetries in this talk, but they're certainly present. The way you would see them in this picture is by looking at the metric in this region. So what you would do is you would take the Kerr metric, and you would Taylor expand it around the event horizon, r equals RH, and then you would keep only the leading components in the Taylor expansion. And that would be a good approximation to the metric in this region. It is a magical fact, which is not obvious in this way of presenting it, that the metric you obtain by just Taylor expanding this one around the horizon and keeping only the leading order components, that in itself solves the vacuum Einstein equations. In this way of saying it, it's not obvious why, but in a second I'll explain it differently and it'll become clear why that must be the case. But one can do this and obtain a metric here, which, as I will show in a second, is the so-called neck metric that I've also written here. And this.
So what's the manifold structure? The neck metric lives on what kind of manifold?
So it's still a four-dimensional manifold.
What's the topology?
It has the same topology as the it's trivial topology, but it's not asymptotically flat anymore. So the Kerr metric, if you go infinitely far away at infinite radius, it looks like Minkowski spacetime. Here, if you go to infinite radius from the perspective of this throat, you're really coming to the mouth of the throat, which is not a flat region. Okay? So I should say that there's actually an enhancement of the symmetry as you go to this throat, which gives you not just an additional dilation symmetry, but in fact even an infinite number of symmetries that correspond to the following picture. So you could imagine taking this cylinder and introducing lines over it. And you could imagine, instead of moving all the lines up and down together, you could move each line by a separate amount. So roughly speaking, as you go around the cylinder in phi, you shift each of these lines by a different amount, epsilon of phi. And that turns out, okay, you have to do more work than just draw this picture, but if you do an asymptotic symmetry group analysis in this region, so using this metric, you will find that there's a large asymptotic symmetry group, which is infinite, and it's generated by diffeomorphisms of this type, which shift these lines by a different amount. The lines also have to rotate in some way, but that's an infinite number of symmetries, and we call that a conformal symmetry. Okay. So the reason I'm bringing this up is to make it clear that there really is an infinite number of symmetries, just as in condensed matter physics when you approach a critical point. We haven't used them yet, but it would be interesting to ask what they can say. I should say that another work by Andy Strominger and Achilles, who's in the audience, some of this infinite set of symmetries was used to make predictions for gravitational waves. Okay. So this was just motivation and picture. And now I'll actually come back and make all of this more rigorous using equations. And then I'll show you a couple of applications. So what I'm trying to say is really the following. Suppose that we have a tensor field with p indices on Kerr. And suppose that it's stationary and axisymmetric. Then let me do the following trick. Instead of writing it in Border-Nyquist coordinates, let me do a coordinate transformation to these new coordinates that are lambda dependent, but they're a perfectly fine coordinate system to write down on Kerr. And then it's a free world. I'm allowed to expand my tensor field in lambda, which is a free parameter that I've introduced here. And generically, the expansion will be of the following form. So it's allowed to be singular in lambda, but let me strip off the divergent piece. It'll have some power h. And then I have a leading piece plus subleading terms. Okay? And the leading piece here, I can extract in this manner. It is obtained by taking the field on Kerr and multiplying it by some power h, which I'm going to call the weight, or conformal weight, for reasons which will be clear in a second, and taking this limit. So this weight h, you can see if it's too large, this will just go to 0. I'll just kill this when I take lambda to 0. If it's too small, this thing will blow up. But there's precisely one weight h for which this leading piece is non-zero and finite. And now this is the leading piece of this field on Kerr as I take lambda to 0. But if you look at these coordinates, when I rescale lambda by taking lambda to c lambda, really what I'm doing is taking t to ct and r to r over c. And so if I do this an infinite number of times, you can convince yourself that when I take lambda to 0, I'm really, in order to keep this coordinate finite, I have to make this numerator arbitrarily small also. And so what I'm really doing is that I'm forcing my coordinate to be localized on the horizon. So this is a scaling limit, which takes me down to this region, the throat. Okay, you can stare at it for a second. So when I take the Border-Nyquist form of the Kerr metric, introduce these scale coordinates and take lambda to 0, I'm really localizing to the throat. And one thing that's interesting is that if I take lambda all the way to 0, I've rescaled an infinite number of times, then whatever I get must be invariant under further rescalings of this form. And so what this means is that if I do a further rescaling, lambda goes to c lambda of this object that I've defined. Because of this property, it must scale in this manner. And using Lie derivatives, I can write the infinitesimal version of this statement in this form. And here I've introduced a new vector field, h0, which is t dt minus r dr. And what this does is that it translates you up and down the cylinder, i.e., it's a dilation of the throat that I've drawn here. Okay? So I've done this for any tensor field, but let's gain some intuition by doing the simplest possible tensor field that we have available, which is the metric itself. So suppose that I started with G mu nu, the metric on Kerr. That's stationary and axisymmetric. It has an expansion of this form, with the weight h being 0. So in other words, if I take the Bohr link with symmetric, I rewrite it in scale coordinates and take lambda to 0, I get a finite non-zero answer, which is precisely this metric, which we call the near horizon extreme Kerr metric, or NEC metric for short. And by the way, in this way of deriving it, it's manifest that it becomes a solution to the Einstein equations. Because all I've done is take a solution to the Einstein equations, do a diffeo, and then take some limit, but that still gives me a solution to the Einstein equations. So incidentally, in this way of thinking about it, rather than the series expansion approach, it's clear that you still have a solution to the equations. And in this case, the weight h is equal to 0, and so you have some metric g bar, which is the NEC metric, plus higher order corrections. And this leading metric, the NEC metric, satisfies this equation for h equal to 0, which is just a statement that this vector field h0 is a killing vector field. Okay? So this is now the rigorous derivation of the statement I was trying to make with pictures, that when you go to the near horizon region in the throat, there's an enhancement of the symmetries. So instead of just having dt and d phi as killing vector fields, you still have a killing vector field dt because the metric is still stationary. You still have a killing vector field d phi because we still have axis symmetry. But the time translation symmetry is enhanced to a larger symmetry, which involves dilations. And this is the simple way to see how this happens. Incidentally, there's another symmetry that appears, h minus, which is slightly more complicated. I do not know of a nice way to illustrate why it should arise. But together, these three killing vectors form the SL2R algebra. So that is what I mean by the global conformal group in NEC. It's the isometry group of the spacetime, and it contains time translations and dilations of symmetries. Now, as I said, I'm not going to go through the analysis, but you could also write down an extension of this group, which is infinite dimensional, and realizes the little story I was telling you in pictures, and that's been relevant for other contexts, but I'm not going to do that here. Okay. So, why is this useful? Why am I doing this? Let's take a step back and think about perhaps a more familiar example of the critical point, which is that from conformal condensed matter physics. So in condensed matter physics, we know that we sometimes have systems which have a knob you can dial, say the temperature, and there's often a critical temperature, Tc, in which we also have a conformal symmetry that emerges. And then what happens is that as I dial into the critical point, as I turn the knob to go to the critical temperature, all my physical quantities, all my fields will have a distinctive behavior, which is of this form. So everything will scale like the power law with some exponent here called the critical exponent. And if you can give the list of all such exponents for the physical quantities of interest to your theory, you've described the physics around the critical point. So all that I'm doing here is really following the spirit and trying to do a critical point analysis for a black hole, and the role of this weight h that appears here is really analogous to that. Another way to say this, if you're more familiar with quantum field theory, is that when you zoom into the horizon, you're going to a region of infinite redshift. So it's like taking an IR limit, and this discussion also exactly parallels the discussion of the classification of infrared fixed points when you flow to the IR, and the classification is made in terms of operator scaling dimensions. And these conformal weights h can be also interpreted as operator scaling dimensions. Okay. So this is the motivation for doing this, and now I'm going to try to show you that it's actually useful and we get mileage out of it. So what do we learn? Here are a few things that we learned. This coordinate transformation as a Jacobian, which is of order lambda inverse. So what that means is that if I start with a tensor field that has rank p, and has p indices, when I take the limit to neg, I get to act with a Jacobian p times. So if I want something that is regular in the limit, I had better not have a weight h other words, if I start with a regular field in Kerr, by which I mean it is in particular regular on the horizon of the black hole, and I want it to be regular as I take the near horizon limit, then it had better be the case that this weight h is less than or equal to p, the weight of the field. Because otherwise, I don't have enough inverse powers of lambda and my Jacobian to keep this from becoming singular on the event horizon. So regularity of fields on Kerr implies this. That's the first thing we can say. And another thing we can say is that if the weight is positive, then all scalar invariants must vanish in this limit. So let me give you an example to be concrete. Suppose I start with a vector field in Kerr, v mu, and let me do this expansion. If this describes something that's regular on the horizon of Kerr, then I can at most have a 1 over lambda here, so h has to be less than or equal to 1. So in the net limit, I'll get an expansion that looks like this. But now, we know that the dot product of this with itself, v dot v, this is a scalar invariant I can build. If this is regular, it should also be regular. But if I look at what happens on the next side, here I will get a 1 over lambda squared, v bar dot v bar, plus order 1 over lambda. And since this must be regular, it cannot blow up in lambda when I take the limit to neg. And so this term cannot be there. In other words, this must be 0. Okay? So the things that we learned by following this analysis are, first, that regular stationary axisymmetric fields in Kerr must have a weight, h, which is less than or equal to their rank. And moreover, if this weight is positive, then all scalar invariants, all the contractions that you can form from the tensor must vanish in this leading piece as you go to neg. Okay? And moreover, the leading piece will satisfy this condition. Now, this condition is actually very powerful because, remember, we're considering stationary fields, so they also obey this condition, since h plus is just d by dt. And these two conditions together are called the highest weight conditions. And they allow us to, they're familiar from representation theory, and they really allow you to classify the representations in terms of the weight h. So in other words, if you haven't seen this before, this is not going to be very useful, but let me just assure you that these are very useful conditions because they really allow you to dramatically simplify, to dramatically constrain these fields. So in other words, start with this regular stationary axisymmetric field in Kerr. If the black hole is extremal, then as you go to the near horizon region, this throat, you know that the leading behavior, the leading piece, will obey these equations. And these equations are very constraining, as I'm now going to show you. They allow you to really figure out what the fields are. So let's do an example. I'm now going to erase this. So suppose we wanted to investigate the electromagnetic field F mu nu. Now, this is a 2 form, so it has p equal to 2. And if we assume that it's regular in Kerr, which I think is a physically well-motivated assumption, then we know that by following this procedure, we'll have an expansion which is of this form. So typically, you can imagine there's a 1 over lambda squared, but actually this is an anti-symmetric 2 form, and if you look at the details of the limit with the Jacobian, it turns out that h cannot even be equal to p equal to 2. It must be less than 1. So here we have p equal to 2, but because it's an anti-symmetric form, h must actually be less than or equal to 1, not 2. So if you take your field on Kerr and you expand it in the limit as you go to neg, generically you're going to have a 1 over lambda piece. This is the leading piece that diverges, plus a sub-leading piece, plus other things. And now you know that the leading piece, F bar, must satisfy this condition for h equals to 1. Moreover, we're interested in stationary axisymmetric configurations, so we also get to impose this condition. And in fact, all of these conditions are really powerful, and they allow us to almost completely determine the leading behavior in this limit. So we have this, we have this, and axisymmetry. Now we want to describe an electromagnetic field, so the form F had better be closed. And we're assuming regularity on the horizon here in the background. And all of these considerations, which are purely kinematic, tell you that F hat must have a universal form, which is the following. There's a free function of theta, which is the one thing that's left undetermined. And then we have this. Okay? So all of this is obtained purely from kinematic considerations. This is the power of this analysis. Now, if you wanted to do physics, you'd still have to, of course, specify the dynamics that govern this field. So what are the equations of motion? And I'm going to show you that if you assume, for instance, that your black hole only has charge current sources that are external to the throat, so they're not in the stored region but slightly outside, then you get a very interesting result, because then what this says is that the current J associated with this F had better be 0. So this F has an associated J, which I'm not going to write down, but it's proportional to A of theta, and it also points in this direction.
So just a question.
Yes?
So naively there could be a function of dr in front of this would have the right scaling properties. So why is this done? Is this extra?
So if you take the neck metric, which I've now raised, but you write down a general 2 form that's anti-symmetric and obeys these kinematic conditions, which we just get from the scaling, you will automatically get to this form. Everything else is
Well,
fixed.
what I'm saying that if you multiply this by a function of dr, it has the right scaling. So I'm not sure what.
No, because you have H plus and H0, the way they act, they both involve T and R, and they completely fix the TR dependence. This is the only TR dependence that you're allowed. Okay, so let me just first assume that my black hole only has charge current sources exterior to the throat. Then the appropriate equation to impose on F and J is that they obey the vacuum Maxwell equations, because there's no sources in the throat. But if I impose the vacuum Maxwell equations, then J bar is equal to 0, which implies that A of theta must be equal to 0, which implies that F bar must be equal to 0. Okay, so this is the vacuum case. So now you tell me, what am I supposed to do? Well, the answer is, that just means that this leading piece has died. Okay? So I'm supposed to say that what was previously the subleading piece now becomes the leading piece, and I can just repeat my analysis. So let me keep going. So the previously subleading piece, which has weight h equal to 0, now becomes the leading piece, and I can just follow the same steps. So now I know that it's still stationary. I know that it's still axisymmetric. It's still closed. It's still regular. Now it has a different weight. It's also invariant under the dilations. So this is very symmetric. And you can write down what the most general such thing is, just from these assumptions. And you get that F hat is equal to a function b of theta dt wedge dr plus b prime of theta r dt plus d phi wedge d theta. And correspondingly, there is a current associated with this, which I'm not going to write down, but is proportional to b of theta, and it points in the phi direction. Okay, so once again, I'm still assuming that the charges are outside the throat region that I'm examining. So I should again impose the vacuum Maxwell equations, which tell me that J hat is 0. And so now this time, I find that this implies B of theta is a differential equation to solve. Can have a piece that goes like QE, which is going to have the interpretation of electric charge, plus a piece that goes like QM, which is going to have the interpretation of magnetic charge, I'm not going to bother to write the function g of theta. It's a little bit complicated, but this is just electromagnetic duality. You can have an electric charge or a magnetic charge. But remember, by assumption, I'm saying that all the charge current sources are external to the throat, so I should set QE and QM to 0. And so what this tells me is that B of theta is 0, and therefore I've also shown that f hat is equal to 0. So in the vacuum case, I've now told you that this leading term must vanish, the subleading term must vanish, and so really the leading term is really proportional to lambda. So now what this tells you is that if you, in this situation, the field in Kerr as you go to neck, as you go to the horizon region, must be of order lambda. But if you take the pullback of this statement to the original Kerr metric, this is really telling you that the field F on Kerr, evaluated on the horizon, is vanishing. So this is the black hole Meissner effect. This is the statement that if you take a rotating black hole and you put some electromagnetic fields in its background, generically the field lines can thread the event horizon and go into the black hole. But now what we're seeing is that if we make the black hole extremal, if it's spinning with the maximal allowed angular momentum, it's just going to expel the electromagnetic field lines. This was known previously before this work, but it was very laboriously derived in Kerr by essentially looking at the vacuum Maxwell equations in Kerr and doing a multipole expansion and proving the statement is true for every single multipole in the expansion. But in this near horizon analysis, you get it very painlessly in 2 minutes. Okay.
So you impose this highest wave condition, which
Yes.
is stronger than Maxwell's wave.
Yes, but I argued that the highest weight condition is necessary. It is just the statement that as you go to this throat in this limit, if you start out with a stationary and axisymmetric configuration, it must split. Its expansion in powers of lambda must split in terms, each of which, as I derived from the argument that I've erased, each of which must obey these equations. So honestly, when we first started this, we were just imposing these equations because of intuition from string theory and ADS3. And we honestly just found it very useful because it made the equations tractable. But we now understand, and this is explained also in this paper, that really these are good physical assumptions to make, and in fact you can derive them from the scaling limit. So okay, this is perhaps not so exciting. Something that's very hard is to actually describe the electromagnetic field configuration F mu in the presence of plasma. So this was basically the topic of Lorenzo's talk, and I'm not going to do better than Lorenzo, but I will say this. So in the assumption where, in the limit where the plasma is collisionless, and therefore well approximated by MHD, we can take a further approximation where it's also dilute. So this doesn't hold, for instance, in the disk or the jet, but perhaps in the region around the jet, numerical simulations seem to confirm that this is a good approximation. And so then you want to impose the force-free conditions, which are just basically the Maxwell equations together with the condition that f dot j is equal to 0. So, okay, so first approximation, if you wanted to describe the plasma around the Kerr black hole, this is a good equation that you could start out by solving, but it's a vexing fact that we do not know of a single good physical solution to these equations in Kerr. They're just so complicated, they're nonlinear, they're coupled. There are only a handful of exact solutions known, but they're not physical. So unfortunately, we're kind of stuck. So one thing you can do again is put them on a computer, and people do this, but at externality you run into problems again. And so the original reason for doing this analysis was to actually see if we could solve these equations in the throat. And indeed, we can. So you just do the same analysis again. You start with the leading piece. You impose these conditions. You see that it must be of this form. This is again just purely kinematics, but now you impose your dynamics equations, which are really these equations, and you try to see what comes out of it. So unfortunately, in this case, the dynamics turn out to be trivial, because you can see that f bar has this factor here, d of t minus 1 of r. Incidentally, this direction is a principal null direction, for those of you who know what it means. And j is also oriented along this principal null direction, so these guys are null. If you with 0. So in other words, in this case, the force-free equation is trivial, and it doesn't give you any information. So this is regrettable. Ideally, what one could have hoped for is that perhaps A of theta would have been constrained by the force-free equations in some form, and then you would have claimed to have found, one could have claimed to have found the universal behavior of force-free plasmas for an extremal black hole as one approaches the horizon. So this was unfortunately not how things turned out. We got no additional information from the dynamical equations, but perhaps one should just impose more constraining dynamical equations.
But
perhaps
you do get a unique solution if you have singularity on the path horizon.
Right, so one thing which is true is that this solution, because I picked a minus sign here, so the principal null directions are d of t plus minus 1 over r. So the choice of minus sign here ensures that the solution is regular on the future horizon. However, it is singular on the past horizon, it turns out. Now, if you imagine a real astrophysical black hole formed by gravitational collapse, you do not expect it to have a past horizon. So perhaps it's not well motivated to impose regularity on the past horizon. However, one can certainly do that. And if one were to do so, then this leading piece would actually be singular and therefore should be rejected. In which case, the force-free equation should be imposed on this piece, which now would become the leading piece. And if you impose the force-free equations on this guy, what they tell you is that b of theta must be a constant. And so if you require global regularity, i.e. both on the future and past horizon, then in this analysis, imposing the force-free condition tells you that the universal behavior of the force-free plasma in this regime is given simply by this two form. And QE, there's some factor of pi into that I'm omitting here. This QE is an electric charge. The problem with this solution, which may or may not actually be fatal, is that f squared, so the contraction of f mu with itself, is negative, which means in non-covariant language that the electric field has a magnitude which is greater than that of the magnetic field, and as Lorenzo was explaining previously, that implies acceleration of charges. Now, one could play the Vlasov equation game and try to really see if this is a problem. It could be that the strong gravity in this region is enough to stabilize the plasma. In other words, because it's electrically dominated rather than magnetically dominated, as is usually the case for force-free configurations, that means that charges will want to accelerate out. But this is a region where gravity is strong, and it could be that the gravitational field balances that out by pulling the particles in. So in order to really nail this, you'd have to use the Vlasov equations, the kinetic model that Lorenzo just discussed. And this is, a complicated analysis, but one that perhaps should be done. So this is what we learned about electromagnetic fields around extreme Kerr black holes by using this analysis. I'm running out of time, so I'm not going to talk about other things, but it's interesting to note that we also analyzed something called the Bagnada-Silk-West effect, or BSW effect, which says that if you have an extreme Kerr black hole, then it is possible to send particles which have finite energy from the point of view of asymptotic infinity, but if you make them collide close enough to the event horizon, you can give the collision an arbitrarily high energy in the center of mass frame. So in other words, to draw a picture, here's the black hole. You send in two particles with perfectly finite energy, and they collide somewhere at some point. If you look at the energy in the center of mass frame, it turns out that if you make this point closer and closer to the black hole, and the black hole is extremal, then you can make this energy arbitrarily large. So this is called the BSW effect. And in this analysis, using weights and limits, it also pops out in just a page. I invite you to look at the paper and see how it works out. But the takeaway is that it's just a generic effect, and if you have an extreme Kerr black hole, there should be very many such collisions around. So the picture that comes out of this entire analysis is that if you have an extreme Kerr black hole, then really what you would expect is here's the black hole, here's the axis of rotation, there's going to be some accretion disk with matter, there's going to be some plasma. As you go to the region around the horizon, this near horizon region, we know what the plasma will do. It will take either this form or this form for some choice of equations of theta that are to be determined by imposing your dynamical equation of choice. And the particles in the plasma will generically collide with the particles in the disk. And by the analysis presented in the paper, one can show that these collisions may have arbitrarily high center of mass energy. And so we expect to see high energy collisions from this region. So that's it for this paper. Let me just announce what's coming next. We really want to make a sharp prediction for the Event Horizon telescope and what they're going to see. And this is the first step in this direction, but certainly one should be able to do better. And we're very interested in talking to people who have thoughts about this. We'd really like to use this type of thinking, exploit the conformal symmetries to make a very sharp prediction about what the Event Horizon telescope will see when they really take a picture. So that will be hopefully in the next year. Thank you very much.
Do you have any constraint on the sign of that QE that you just erased, or it's just a parameter? I was thinking like if you...
No, it's just a parameter.
Because if you have electron-positron, for example, with the gravity and an electric field, you'll only be able to balance one species, right? Not both.
I actually think it's very counterintuitive, but I don't think that's the case. You can have stable circular trajectories for charges of either sign. And if you've ever looked at ADS2 electric fields, this may be familiar to you, but it's just a property of the Sneck metric. It's more like ADS. It's not asymptotically flat. So I should say I've tried pretty hard to prove the stability of this plasma, but I haven't succeeded yet. So I'm still trying. But that's not an obstruction. I think it probably
I was
solve the
mostly
Lazarov equation.
thinking about radial inflows, but like you're saying they're like stable, sort of like rotating orbits. So
Yeah, they
quite
exist
possible.
for both sides of shard.
Any further questions? Let's thank the speaker again.
Thank you.
Let's absolutely thank the organizers for putting this together, because I'm sure it was
conference, I think we will continue some more conference like that because a black hole initiative has been approved and Andy is here. So we will be much more interaction with Smithsonian and also astronomy departments here. And there are about 2,000 square feet upstairs on the second floor. They are using the office. So I hope you guys will come again to have some more workshop like this, which I think is good. Thank you. Tangible. The view.
Thanks for coming.
Really, amazing. Okay, I would love that. And you know, also, I should tell you, there's a paper coming out this week. Yeah, so we managed to do that. We have a paper. I found new solutions.
No.
Thank you.
Fast laboratory.
So fast. least for 2 years.
no jet.
Because
The
you will.
spectrum is mostly coming from the signature is mostly coming from the disk. No jet. And then there are periods in which the disk is very tenuous, more like about speed, and there are like very powerful jets. In transitioning in between, there is like a whole variety of like phenomenology that is neither oriented toward judging the possible. It is quite possible that the black hole is transition. The reason why we can follow this solar mass black hole.
Wow, I mean, that would have been, I didn't want to put you on the spot.
No, generically they're supposed to be
Generic.
Cycles of like this.
Yes, we know a lot about this. So,
Okay,
so
I mean, the jet is fed by this.
But I mean, there is no disk in the center.
The disk is very underloaded. There is a thick disk. Geometrically, this is a favorable configuration for the jet. Generally, the jet needs disk for feeding the material and the black hole. The jet is supposed to be what we know now from giant structures that are seen by the Kerr telescope. Energetics not explain with stars being powered by it. Reasonable explanation is that the black holes itself are powered through a jet. The jet is not very young. So these structures are old. Hundreds of years of years. It's a difference that the jet is somehow present to the dark. The reason why it's switched off. But I think there is evidence that the jet at some point came out like a but they're all in. And for the spin, we will really have to wait like even more. There is a couple of years we do have images already. Like with just space reference. From the center of the black hole is actually on scales that are smaller than the this is used to insert orientation of the disk with respect to the line of sight. This can be either the black hole is non-rotating, and then the disk is just whatever the feeding material keeps it circular momentum, or that the black hole is rotating and this is the but the two things are still possible. Either no rotation and rotation is done by the dark scale spinning of the black hole, or actually DPR is also
they don't constrain the coefficient of
basically the
well, that's just simply that
it's a very specific like this is also I started that paper and I went through that one. The reason why the ADM was projected over. It's using tomorrow. Let's make sure we have to. Why don't you hear from me on Thursday?
So I can talk about my
tell me.
hopefully I just took
Maybe you're proving it.
the spin meters, I think you're fully right. So I had in mind the people that say the spin was zero because they have seen Chandra jets.
Yeah, I feel like
These are all interactive.
No. What happens is,
Like Bagano,
and then what do they get? Put it down.
No.